This is the last part of our electricity or electric circuits module, and we're going to talk about the final formula that you need to know, which is the formula I squared R, power equals I squared R, and then we're going to apply some of these ideas to a normal question and then something in a kettle. So not a long lesson, but we do actually do a little bit of maths in this. So first up then, if the kettle uses 230 volts and has a resistance of 20 ohms, can we calculate the current in the kettle? So here we go. Well, we know that I equals V divided by R. That's from Ohm's law, which V equals IR. So I've just rearranged it. So I'll put the numbers in. I equals V divided by R, which is 230 divided by 20, given the question, which is 11.5 amps. So the power output from the kettle would be P equals V times I, another formula that you need to learn. Power equals voltage times current. So again, we've got 230 in the question. We've just worked out 11.5 amps. So we've got a power of 2,645 watts. So now, can we derive a formula that links power to resistance and current instead of voltage and current? And then if we do that, can we check it using the figures in the questions above? So we know that P equals V times I, and we also know that V equals I times R. This is Ohm's law. So we've used both of these in this question. So P equals V times I, but V equals I times R. So if we put I times R where this V is, we end up with P equals I times R times I. So P equals I times R times I. And of course, if you go I times I, you get I squared. So there's a brand new formula, which is P equals I squared times the resistance R. And you do need to learn that formula. So can we just check it? Well, using the idea above, we add an 11.5 amp into the kettle, so 11.5 squared times the resistance of the kettle, which we were given as 20 ohms. And if we do 11.5 squared times 20, we of course get 2,645 watts for the power, which is just what happened here when we did it a longer way. Okay, so you need to be able to use that formula. An example from a textbook using this formula: if the motor in a toy car has a resistance of 25 ohms and an operating power of 64 watts, find the current it draws from the battery. You don't know the potential difference, so you're going to have to use P equals I squared R here. We haven't got V, so rearrange the P equals I squared R equation for power to make the current the subject. Now this is, some of you might find this tricky with maths, so I've divided through by R, so I've got P divided by R, and then I've taken the square root of both sides because I'd have I squared equals P times R. So if I square root both sides, I end up with the square root of I squared equals I, and the square root of P over R, is the square root of P over R. So once you've got the formula, I equals the square root of P over R, then you put the numbers in. So I equals the square root of 64 over 25. And if you put that in your calculator, you'll get an answer of 1.6 amps. Okay, so just to finish, I thought we'd do a question about a kettle again. So this time we'll use the values for the maximum current and voltage a mains kettle could possibly have. And we're going to calculate the best value of the resistance needed, the power output of the kettle, and the time the kettle would take to heat 1.5 kilograms of water from 20 degrees when it comes out the tap to 100 degrees boiling. So the first one, the best value of resistance needed, well, R, the resistance, is equal to V divided by I. If this is a mains kettle that you're going to plug in, doing a bit of revision here, then 230 volts is the mains electricity, and 13 amps is the maximum current you can have in a normal plug socket. So the resistance is 230 divided by 13, so the resistance of our kettle needs to be 17.7 ohms. Okay, now the power output of the kettle, we're going to use P equals I squared R. So I squared is 13 squared multiplied by the resistance we've found, 17.7. So 13 squared times 17.7 is 2,990 watts. Now, part C, the time, how long would this take to heat 1.5 kilograms of water? We need to remember specific heat capacity equation. Now, the specific heat capacity equation tells us that the energy required is equal to the mass times the specific heat capacity times the temperature change. Now, with this, we know the mass of water is 1.5 in kilograms. We know the specific heat capacity of water, you'll be given that as 4,200 joules per kilogram per degree C, and we know the temperature change is going from 20 to 100, which is 80 degrees. So we've got 1.5 times 4,200 times 80 degrees. If you do all that, you get 504,000 joules. Now this isn't the answer because we need the time it would take the kettle to do this. Now using another formula, we know that power is equal to energy divided by time. I'm just going to rearrange that and say that time is equal to energy divided by power. Here's our energy, 504,000. Our power's 2,990 that we worked out. So if you divide those in your calculator, you get a time of 169 seconds. So this is taking, what's that, nearly 3 minutes to boil this kettle, which sounds about right. Okay, so you can see how as you progress through the physics course, you would be expected to use different parts of your knowledge gained in different units to answer some of the trickier questions.